In this problem, we're going to be looking at the rectilinear kinematics of a particle. So we've got a particle that is moving through an electric field from one plate to another. And the velocity profile of this particle has the shape shown in the figure. We're given some information about Vmax and the time scale in the figure, and our goal here is to draw the position and time graph and the acceleration versus time graph for the particle. Okay, so there's a couple ways to look at this. And we're going to start with a step 0, which involves making some observations and developing some expectations about what we're going to be able to see. But before we do that, let me just go ahead and write some things on the figure just for clarity. So we're told that our time scale here, t prime, is 0.2 seconds, which makes t prime over 2 0.1 seconds. We're also told that our Vmax here is equal to 10 meters per second, and it's not represented on this particular graph because this is a velocity versus time graph, but we're told that s equals to 0.5 meters at time is t prime over 2, which is 0.1 seconds. So when we draw our position versus time graph, the so-called st graph, we're going to need to make sure that that information is captured on that graph. Okay, that being said, let's go ahead and write an approach about how we can solve this problem. So I'm going to insert a step 0 here, which is observations. Now you see this sort of step 0 frequently in these videos because there are many problems where it's very sort of straightforward to sit back and look at the problem statement and develop some expectations about how you think the problem is going to go. This gives you some intuition about how the calculations go, and it also gives you a point of sort of checking so that when you get an answer as a result of calculations, you compare it with your expectations, and that gives you some confidence that what you've done is correct. And we'll make those observations in a moment. We know that step 1 then is to consider the equation for Vt. We have a graphical version of it, but we don't have an equation which is written in terms of time t. And then once we have that equation, we're going to go ahead and derive an equation for s as a function of t. And from that equation, we are going to be able to draw the st graph. The third thing we're going to do is we're going to take that velocity equation from step 1 and we're going to derive an equation for the acceleration as a function of time, and from that equation we are going to draw the AT graph. Okay, so we've got 4 steps here. The first one is an important one. It's observations. That's what we're going to do next. So step 0 here, observations. Now, off to the right here, I'm going to construct what I think the S, the V, and the A graphs are going to look like. So let me put up here a set of axes. Just sort of draw this off to the side here. So I'm going to start here. There's my time axis, and this is going to be acceleration. And then I'm going to put another time axis here. There is my velocity, and then another time axis up here. And that top axis is going to be my position. And then I'm going to put in 2 dashed lines to correspond to the relevant times. So let's say that's t prime, that's 0.2 seconds. And then over here in the middle, that's t prime over 2, that's just 0.1 seconds. Now in blue here, let me sort of draw in what we already know, and that's the information about v. So v is linear from 0 to 0.1. It's got a positive slope. And then it's linear again from 0.1 to 0.2, but it has a negative slope. Okay? So that's what we've got so far. Now the question is, how can we go about sort of figuring out what we think S and A are going to look like? Well, in order to do that, we can just write some basic equations that we know to be true. So for example, we know V is going to be ds dt, and we know A is going to be dv dt. So if V is linear, that implies that A is going to be constant. And it also implies that S is going to be somehow second order. Okay, it's going to have a second power dependence on time. And based on what we know about v, we can make some conclusions that look like this. So let me draw the speculative stuff in red. So if I go to the A graph over here, we know that the derivative of the v curve is going to be constant because v is linear, and we also know that since the slope of v is positive from 0 to 0.1 seconds, we know that A is going to have some constant, and it's going to be positive. And then by the same token, we can look at the velocity profile between 0.1 and 0.2. We recognize it's got a negative slope, and so we think that the acceleration is going to be down there somewhere. So you can see that there's going to be this sort of discontinuity in the acceleration as we go through time equals to 0.1 seconds. So that's our expectation on acceleration. It's kind of skew symmetric with respect to that center line at 0.1 seconds. Now, the S curve is a little bit harder to visualize, and you may or may not be able to see this, but because of the nature of this, we know that there's going to be sort of an inflection point on S because V changes slope. We know there's an inflection point sort of here at point 1, and up to that point, the curvature is going to be concave up, and after that point, the curvature is going to be somehow concave down. So I didn't draw that exactly really smoothly like I wanted to, but you get the idea of what's going on here. And we know from the problem statement that this is going to be S equals to 0.5 meters. Okay, so however we solve this thing, we know that that's what it's going to look like. Okay, so we don't know this value up here, let's say, just yet. We know S is going to start at 0, and we don't exactly know the shape of that curve yet, although I've captured the curvature of it, I think, correctly. So what we've got here now is some expectation about what's going to happen. Let's go ahead and use the mathematics and actually use whatever equations are relevant to go ahead and see whether we've got this right or whether we've got this wrong. So step 1. Let's go ahead and write an equation for the velocity as a function of time. Okay, so we've got a couple of things to think about here. Let me go back to the original picture and we'll make some observations here. So we know that V equals 10 meters per second at t is 0.1 seconds. And we know V is equal to 0 meters per second at t is equal to 0.2 seconds. And so since these are linear on the graph, we figure that we need to know something about this slope right here, and that's what we're going to do next. So if we look at the slope of the V curve, we find out that it looks like this. There's time, there's V, comes up in a linear way up to there. This is 0.1 seconds, and this is 10 meters per second, so that the slope is really just equal to 10 meters per second divided by 0.1 seconds. So that's equal to 100 meters per second squared. And what this indicates is that V of t is just going to be equal to 100t. It's got units of meters per second, and that is valid for 0 t to 0.1 seconds. Okay, so that's our first equation. Now, the question is, what happens after that? Well, there's a couple of ways to look at this. I'm going to write it one particular way. There are other ways you can write this as well. We know the slope on the other side of that, the post 0.1 second part of it, is going to be negative 100 because it goes back to 0. So V of t then is going to be V max, which is 10 minus 100 t minus 0.1. Again, that's going to be in meters per second, and that's going to be good from 0.1 to 0.2 seconds. So now that we've got our equations for V, which are valid over the entire domain, we can go ahead and move on to step 2, where we begin to construct the S versus t graph. So step 2. We're going to try and derive an equation for s as a function of time. So the way we usually do this is we write an equation which says v is ds dt, and then we kind of separate that. We say ds is equal to v dt. And so then we turn that into an integral, of course, which is an integral from 0 to s of ds. That ends up equaling a 0 to t integral of v dt. And so we have an equation for v. In fact, it's defined in two parts, so we can go ahead and piece together what we think the total displacement is going to be based on integrals of those two parts. So let's start with 0 to 0.1. The equation looks like this. S just turns out to be an integral from 0 to t of 100t dt. So that just equals to 50t squared. Okay, and we know from the problem statement that at t is equal to 0.1 seconds, we know s is equal to 0.5 meters. And indeed it is, if we plug in t is equal to 0.1 seconds. So that worked out okay for us. Let's go on to the next phase of this, and that is from 0.1 . So let me write this integral without inserting the bounds of integration for a moment. On the left-hand side, we're going to get ds, and that's of course an integral over some bounds. On the right-hand side, we're going to get an integral of 10 minus 100 t minus 0.1 dt. Now let's talk about the bounds of integration. On the left-hand side, we know that at t equals to 0.1, we have s equals to 0.5, so that's the lower bound of integration. And then the upper bound of integration is whatever s maximum is, and so that's sort of what we're solving for. On the right-hand side, we know this goes from 0.1 up to t, and so I'm going to go ahead and keep that as an integral over t, and you'll see how this unfolds as we go along. Now you can make another choice here. You could put in a 0.2 and go ahead and do the integral, but I'm going to show you sort of symbolically how this turns out, and then we'll plug in t equals to 0.2 a little later. Okay, so let's go ahead and do this integral. On the left-hand side, we get s minus 0.5. On the right-hand side, it turns out to be 10t minus 50t squared plus 10t. That's all going to be evaluated from t down to 0.1. And so when we do this, we get s minus 0.5 equals to 20t minus 50t squared. And then we subtract off the values when we substitute in 0.1 for the time, and that turns out to be 2 minus 0.5. When we do all the math, we get s turns out to be equal to minus 50t squared plus 20t minus 1. Okay? And then at t is equal to 0.2 seconds, it turns out that s just turns out to be 1 meter. Okay, so if we go to a clean page here, now we can construct what the S curve is going to look like. So the ST graph is going to be something like this. Okay, so there's time. Here's S. Let me put up some dashed lines here. So there's 0.2 seconds. There's 0.1 second. We know we're going to have a point here at 0.5 meters, and the graph is just going to come up here somehow like that, and then over here, and this is going to be 1 meter. And it's a nice smooth curve, a lot like the one we showed in step 0 when we had intuition. Let's go ahead and do step 3 now, where we write an equation for the acceleration, a as a function of time. Now this is a pretty easy one because we know that the velocity is a linear function of time, which means the acceleration is constant, and the acceleration is just the value of the slope of the v curve, as we described before. For 0 to t to 0.1, what we're going to get is the acceleration as a function of time is positive 100 meters per second squared. That was the slope of that first part of the curve. and then from 0.1 to 0.2 we get the acceleration is negative 100 meters per second squared. And so if we draw that, we're going to get something that looks like that. There's t and there's a. Let me put up some dashed lines here. So this is 0.2 seconds. This is 0.1 seconds. And we can go ahead and say that this one is plus 100 meters per second squared. Over here we've got minus 100 meters per second squared, and it's sort of skew symmetric, just the way we thought it was going to be back in step 0. So let's go back and review what we did. In this problem we had this particle moving through an electric field with a velocity profile which was linear. It was sort of a triangle wave. And the first thing we did that was useful is we developed some observations. We knew the shape of the velocity curve, and we know its relationship to both the s and the a curves, the position and acceleration curves. And so we were able to take a guess at what we thought was going to happen here. Then we went through and used some mathematics to go ahead and define the v curve, integrate to find the s curve, which we did here, and then differentiate to find the a curve, which we did here. And we found out that our intuition that we did back here in step 0 was indeed correct, and we had a second order position curve, a linear velocity curve, and then a constant acceleration curve.